FAA presents Jim Bede, designer and builder of new types of airplanes for general aviation. His sensational bullet-shaped Bede 5 has become one of the most publicized sport airplanes ever introduced. Here on videotape, he discusses topics common to all aircraft design.
This session will be on high lift devices. By high lift devices, we're talking about both trailing edge high lift devices as well as leading edge. Those two areas are the areas that you can influence greatly the lifting capabilities of any particular wing. Trailing edge high lift devices are commonly called flaps. We have a series of different types of flaps. One is a split flap. Split flap basically is nothing more than a standard airfoil section with a portion of the lower section capable of hinging at some particular point and being deflected downward. A DC-3 is a good example of a type of airplane that has a split flap. The lower portion comes on down and produces a reasonable amount of a lift increase. Not the most powerful one, but a relatively efficient one. The split flap has one real nice characteristic in that it produces the minimum amount of pitching moment, of extra pitching moment of the airfoil section itself. And in some cases this is quite important and quite helpful. There's sort of a variation of this called a zap flap, where this thing pitches down like this and then moves back a little on the track. But frankly, the advantages of that are so slight that I don't even know of hardly any real successful application of that type of flap. But the normal split flap is a fairly effective flap operation. It is not the most powerful one, but it does a reasonably good job. A second type of flap is called a plane flap. This is one where basically you have nothing more than a hinge trailing edge similar to an aileron. It pivots and deflects downward. A plane flap is a little bit more effective than a split flap, but not that much more. And it's relatively simple to manufacture. You have a hinge point inside the wing itself, so you do not have any external brackets or anything like this. The load on the flap, the hinge moment load, so therefore the load of activating it, whether it's electrical, hydraulic, or just manual, is a little bit higher than a plane flap, but not too bad. Obviously, the length of the cord of any of these flaps controls the amount of lift. We can go into that in a little more detail later. The next type of flap that could be used is what is known as a slotted flap. A slotted flap is somewhat similar to a plane flap, except that there is a slot that is controlled between the flap and the main wing section itself. And in this particular case, generally speaking, you do want to hinge it at a point that's outside the airfoil, generally at a position somewhat lower than the bottom skin of the wing, and therefore you probably have to end up with a bracket assembly that will control the flap. And then this flap pivots back, and in the deflected mode, will look like this. Now what happens here, when the flap is down, and let me take care of the one that's up in there so we get a little better look at this thing. What happens here is this slot, and it has to be very, very carefully built and laid out. When you check on the data and look up flap designs and characteristics, you have to follow the coordinates of this slot arrangement rather important because it's critical. But what it really does is when you're flying at a high angle of attack, the bottom air here is under high pressure. It comes around through the slot and really becomes almost a boundary layer control device on the flap section itself and produces considerably higher lift than the normal split or plain flap would do. The slotted flap here is a very common flap, a very good flap, a very effective flap. The one that we have that would be better than this would be a double slotted flap. And really, what that comes out to be is something very, very similar to the single slotted flap, except that the flap itself, and I'm just going to draw this flap now in the down position, has two slots essentially in it. First, you got the flap section itself, and then a little auxiliary airfoil built into it. This is connected directly to the flap itself. The two units work as a unit. You have one slot here and a second slot here, and that's, of course, where it gets its name, double-slotted flaps. This is a very effective flap, probably the most effective flap, based upon the total area, but it is complicated to make, rarely seen on general aviation airplanes, but very, very common on commercial airliners or military-type fighter aircraft or something like this. The double-slotted flap will probably give somewhere in the neighborhood of 10 to 15% increase over what the single-slotted flap would be. The only time I would really recommend this is when you have an airplane where you're absolutely trying to get the maximum possible lift coefficient out of the particular wing area you have, and then the double-slotted flap itself has its benefit. There are some careful considerations that have to be done, because where the flap actuates from, the hinge point is very, very critical. The slot layout is very, very critical. But if done right, and there's a lot of data on it, so you can determine exactly how to do it, if done right, it will work very, very well. The only follow-on to this type, and the only one that in one sense gives more lift than the double-slotted flap, is the Fowler flap. And a Fowler flap is very similar to a single-slotted flap, or it can even be made with double slots to it. It's just that the Fowler flap is built so that it goes within the wing section quite a bit, and when it is deflected, when the flap is deflected, it moves back here, and therefore is actually increasing the wing area of the wing itself. So therefore, now let me redraw that a little bit so it gets a little bit clearer. The Fowler flap extends the chord of the wing itself, and there is actually more planform area being exposed right now, but it in effect is a slot, does the same thing as a single slotted flap, and in fact what you will find out that the data that's presented on Fowler flaps is a increase, a delta CL because of the flap, but it's all based upon the original area. If you take into account the increase of wing area, you'll find out that the delta CL, the increase in CL due to the flap, is about the same as a split flap, or excuse me, a single slotted flap. So therefore, these two flaps, the single slotted flap and the Fowler flap, are essentially the same, but the advantage of the Fowler flap is that you actually have more area exposed. A Lockheed Connie, P-38, a lot of Lockheed's airplanes use the Fowler flap. The disadvantage of this is the fact that you probably have to have a track assembly to activate this flap, and that's much more difficult to make. Involves rollers and cams and other assemblies to it, which can present maintenance problems that go with it. But these basic flap designs are the typical and common trailing edge high-lift devices. There's a very good report done by NASA, done in 1949. It's TR 938. That's TR 938. This report is a complete summary of all of the trailing edge high-lift devices. And it not only explains what the lift coefficient you can expect out of it, it talks about the drag that the flaps produces, talks about the hinge moment that the flap itself has on it, all of the other various characteristics that you could expect. the profile layouts, the design itself of the slot, the particular configuration it has to be at, and where the hinge moment has to be. In addition to the trailing edge, we do have leading edge considerations to be taken care of. Let me clear up one point, however, before we get to the leading edge portion of the thing, and maybe try to, anyways, clear up one conception that, or misconception that seems to be around. Most of the time when someone sees a wing configuration, let me draw this one, all right? Let's draw it at an angle of attack already, assume that the wind is blowing in here. And we have a wing that's deflected, and we'll put a single slotted flap on it. And we have it here. What's going to happen is the air is going to flow, going to come up over the wing, and going to speed up and come down the trailing edge here. The air on the bottom will, of course, be deflected down too. What this will do will produce a lift pattern that is something like this. These could be visualized as vectors demonstrating how much lift is being exerted or force being exerted on the airfoil. A lot of people believe that when you deflect the flap down, that it produces a low pressure above the surface of the wing of the flap itself, and that produces lift. Yes, it does. But what's most important about the flap is that it induces a great deal more air to flow over the wing, and therefore makes the leading edge of the wing lift a lot more than it did before. This is why a split flap works. When a split flap comes down, there is no low pressure region on the flap itself to produce lift, but what it does do is induces a great deal more air to flow over the top of the wing. It forces it to come back here, forces it to come over there. So when you deflect the flap, you really make this portion of the wing work harder and better. And you can increase the lifting power of the wing considerable. I mean, you can go from a lift coefficient of 1.6 unflapped to lift coefficients of 3, almost doubling the total lift. And even higher, in fact, by going into a really proper design. Well, if you're going to increase the forward portion of the wing to lift more, to have the pressure get lower, to have the airflow flowing over better, you have to watch very carefully what's happening to the leading edge itself. So this is where we come into leading edge devices. If your particular airfoil section you picked happens to have a relatively large leading edge radius, you could probably end up with some pretty good flaps and do nothing to the leading edge itself. But in most cases, what will happen is the flap will do all the good it can possibly do until the air coming over the leading edge cannot maintain that curvature, has a flow separation, and basically the wing starts to stall. Most airplanes are equipped right now with trailing edge devices, I'm talking about general aviation airplanes, are equipped with trailing edge devices which will increase the lift of the wing, and they let it go at that. But a definite increase, maybe 20, 30, even 40%, can be recognized by doing something to the leading edge. On the leading edge, we have several categories of devices that can be incorporated. One is a fixed slot, where a gap is designed and made right into the airfoil itself and left there as a fixed opening. This will very definitely increase the lift of the wing. It provides a slotted effect, a boundary layer control effect of the air coming up over the wing and preventing it from separating. Definitely it will improve the lift of the wing. It will improve the lift of the wing even without flaps on it. Most of these leading edge devices we're going to talk about now will increase the CL of the wing without even using flaps. But since flaps are relatively easy to build and install, it's not real wise to only use leading edge devices. You should use them in combination. The thing that's wrong with this system, the fixed slot like this, is that it increases the drag considerably. It's just about doubling the drag of the airfoil section. And this is doubling the drag of a standard 4-digit or 5-digit airfoil section. Of a laminar airfoil section, it might even triple the drag coefficient of that section. So it's not too wise to use this type if your airplane has any kind of thought of having decent cruising speeds. by all means you want to go to something different than that. Well, what is different? Well, you could go to a adjustable leading edge slot whereby the surface moves out on a track similar to that. Now you can see that you have just about the same advantage you have as you get to high angle of attack. As the air is flowing in this direction, it will then be vectored through this slot and up over the top of the wing, preventing the leading edge from stalling to a much, much higher angle of attack. This unit, however, has to slide on tracks of some sort. You would not want to make an external hinge out here to do it, because that's a spot where it would cause a great deal of drag and possibly more flow separation anyway, so it has to be an internal type of device. It's not real complicated to make, but it still has to be done with care. Where this slot is, what the shape of that nose, what the shape of these corners here is very critical, but there are a number of reports that are available that will tell exactly how to design it, how to shape it. So the movable slot is a very common one, a very popular one. A heliocarrier used it on an entire wing. Now these movable slots can be designed in several ways. One, they can be designed so that you literally have a control within the cockpit that you can move and crank or operate to deflect the flaps, the slot. It could be hooked into your flaps itself, so when you put the flaps down, so do the slots come out. Or like a heliocarrier, by designing it properly, you can actually make it so that it is essentially spring-loaded to close, but as you get to the certain angle of attack, as the air loads on the little fixed surface up front get high enough, it sucks and pulls the slot out into the open. And I don't know how many of you have ever flown in a heliocarrier, but as you get it up near stall, you can actually see, you'll be sitting there, one slot will open and close, and they'll sit there and move back and forth if you're right on the edge. Has no adverse effect on the airplane trying to roll around. It doesn't change the lift coefficient or the angle of attack or anything else. It's really nice, quite nice to see the way they will go in and out in that particular manner. That's a very common and very nice method of incorporating a high-lift device on it. Another type of high-lift device, which isn't used too much on general aviation airplanes, but used very commonly on airliners, is what is known as a Kruger flap. Basically, this is a section of the bottom of the wing which is hinged right at the surface, and normally they put a little round leading edge to here, because what this flap will do is hinge here, and it will extend out like this. Now this looks a little bit strange, but it does provide, in a sense, a new curvature for the air to flow over the leading edge. You would not want to use a Kruger flap on a airfoil section that, say, is 12 or 14 or 15% thick, because really with any airfoil, your leading edge radius is already big enough. But when you're dealing with really high-speed airplanes where you must have a thin wing and you must have a relatively sharp leading edge, the Kruger flap can work reasonably effective. The Kruger flap will have a flow separation right behind the leading edge in here, but as the flow comes on the bottom, this separation will not be bad, because what it's actually going to do is be pushed right back up to the surface and flow along the bottom of the wing. You actually can feel turbulence within the airplane when the Kruger flap comes down, the leading edge flap like this, and there will be some vibration, but it's not a situation of flow separation like you have over at the top of the wing. Another type of leading edge device, which isn't really used too much, but has some real potential, I think, is essentially an expanded leading edge. I think it was B.F. Goodrich developed one, and I'm sure there's others have done too, where basically you can have a rubber boot on here that comes around and then inflated to expand and bulge. Now what this does is put a very, very large leading edge radius onto that airfoil. It's smooth and can produce a significant increase in the CL of the wing by having a very large leading edge radius like this. And of course, if it's adjustable so that you can collapse it back down to the original profile, then you have no penalty at high speeds whatsoever. Now, there are some aircraft designs whereby you want to take a standard airfoil and put a bulging leading edge to it like this and leave it there as a fixed entity, in certain portions of the wing to delay the stall of that particular section of the wing. But if you leave it, of course, you've changed the profile of that airfoil, and in most cases have increased the drag. But in some cases, the compromise is well worth it. There's a couple maybe things that should be remembered and recognized about the two devices, the leading edge flap and the trailing edge flap. And this can be demonstrated best by looking at the lift curve slope. Lift coefficient versus angle of attack. On a normal airfoil that's cambered, you will have a lift curve slope that will come up and go down like this. If this angle of attack that stalls is, say, 16 degrees, and if the lift coefficient, maximum lift coefficient is 1.5, we will see that typical kind of pattern. I'm going to erase this portion up here to give a little bit more room, because what I really want to demonstrate is this. This is a planed ordinary wing section, and if we put flaps on it, trailing edge flaps of any type, split, single slotted, Fowler, whatever it might be, it basically lifts this curve up and moves it into a new section like this. But in most cases, the angle of attack that the wing will stall at will be pretty much the same. And this is somewhat understood in the fact that here you are with the trailing edge of the wing, you put these devices to induce more air to come over it, but the wing itself can only go to so much of an angle before the flow over the leading edge causes separation. So the flaps produce a lot more camber, a lot more lift, but not changing the angle of attack itself. So this is because of the flap at the trailing edge, and the leading edge, on the other hand, assuming you don't have flaps on it, will take this original curve and extend it to maybe 22 degrees angle of attack. So without flaps in the back, if you put a leading edge extension, you're going to take the standard lift curve slope and just continue it on to a much, much higher angle of attack. Obviously, if you use the both together, you're going to have this effect. You can see that, let's use a colored one here, that the distance from here to here, this delta CL, is due to the trailing edge, and the distance from here to here, this delta CL, is because of the leading edge extension. Trailing edge flaps and leading edge flaps are very, very powerful devices and very useful, and really should be used on practically all aircraft designs. There's some places where obviously you don't want to use them. A sailplane. Sailplane ends up with a lot of wing area, high aspect ratio wing. It doesn't really land at a low speed. It doesn't need to land at a low speed. It has a relatively low wing loading already. Therefore, a trailing edge flap for high lift devices is not practical. Now, you may want to use a trailing edge flap there for a couple other reasons. One, you may want to use it as a spoiler. You might want to deflect it 70, 80 degrees, for example, not just to produce more lift, which if it's small and chord may not produce all that much, but it will definitely give you more drag. Another thing you can do with it on a sailplane is you can adjust the trailing edge so that it's in the zero position in one case, but literally move the flap upwards 2 or 3 degrees, and this will change your lift curve slope up and down a little to give you a better balance on it. But in a sailplane like that, that's for an entirely different reason for it. An all-flying wing, for example, however, has a difficult time in using the flap, because by putting the flap in the trailing edge, you generally will produce a pitching moment that is greater than what the flying wing's stability characteristics can tolerate. Northrop, when they built the B-35 and the B-49 flying wings, they needed to use some form of flaps on there. And what they did, they used a split flap. But even in that case, they could not use the split flap all the way back at the trailing edge. And what they really did do is this. Let's draw the flying wing from a top view. It was swept back, with the outboard sections here becoming ailerons and roll control. And they used the flaps in this inboard region here, and it was somewhat forward already with the center of gravity probably being located here. But they took the split flaps, because it's the one that has the least amount of pitching moment, and they moved it somewhat forward on the bottom of the wing. I don't remember the exact numbers, but I think the hinge line was somewhere around the 60 or 65% chord. And by deflecting the flaps down in here, they got an increase in CL in this region of the wing with minimum pitching moment changes and ones that they could tolerate with it. But no way could you put large trailing edge flaps on a flying wing way in the back, single slot or something like that, and try and deflect it. It'd be impossible for the aircraft stability characteristics to tolerate that much of a center of pressure shift. So that's impossible. But any other airplane, whether it's a general aviation airplane or a high-speed fighter or an airliner or something like that, flaps are a very important and very critical thing to use. In addition to that NACA report 938, there is another report that came out slightly after that called TR 942. Now 942 title is Investigation in the Langley 19-foot pressure tunnel of two wings of NACA 65-210 and 64-210 airfoil sections with various types of flaps. Now, that particular airfoil is a low drag airfoil section, laminar flow section, and since it's a 210, it doesn't have a great deal of camber and it doesn't have a great deal of thickness to it. But it's a good report because it shows all the different types of flaps with different types of plan forms and how each one of these flaps affect the maximum lift coefficient, how it affects the stall pattern, how it affects the pitching moments and the loads on the wing and everything else. So that's another report that I definitely recommend. Even though that report doesn't apply directly to some of the applications that someone would use in a general aviation airplane or home-built airplane, it gives you a real good indication of what you can expect with it. This is a chart that shows the variation of the maximum lift coefficient with different flap chord ratios. This particular chart happens to be in using a 230 series airfoil. The bottom one is for a 12% thick airfoil. The top one here is for a 21% thick airfoil, and the very top is for a 30% thick airfoil. That part's not important, nor even the airfoil section, but the thing to notice here is this. Here is the increase in lift coefficient, the delta CL. This is only 10% of chord of the flap compared to the whole wing, and yet you get a sizable increase. When you go from 10 to 20%, you get an increase, but not that much. You can even go 30 or 40% chord, and on a 12% thick airfoil, you've hardly gotten any benefit of the increased chord of the wing. So therefore, a trailing edge flap having a chord of the flap equal to 10 to 20 to maybe 25% of the chord of the whole wing is the best region to be in, and you will get the maximum benefit that is practical. In dealing with a plain flap, one again that's just a little bit better than a split flap, sealing the gap between the flap and the wing has a definite effect. Here is a chart that shows the maximum lift coefficient as compared to flap deflection for a simple flap on a Clark wire airfoil, one with the gap open and one with the gap sealed. Now this particular flap is 20% of the chord of the wing. And here it is with the gap open, you get an increase from 1.2 to a little over 1.6. But by sealing the gap, which even gives an increase in lift coefficient flaps up by sealing the gap, you can go from 1.26 on up to about 2.0. So this is an important thing to remember. And whether it's a Clark wire airfoil or a 4-digit series or a 64 series laminar flow, on a plain flap, and this is true for an aileron, on a plain aileron, sealing the gap has a definite improvement both in maximum lift coefficient, flaps up or flaps down, and even on drag. So sealing the gap on that type of arrangement is quite important. There are several references I strongly recommend, one of which is Theory of Wing Sections. This is a very popular and very useful reference. It's based upon NACA's 1945 report, TR 824, but it has even additional expanded information in it, but tremendous amount of data on airfoil sections, wing planforms, high lift devices, and so on. It is a very useful and very practical book that I highly recommend, and it's modestly priced. Another new book that has recently come out is The Design of the Airplane by Darrell Stinton. This is an extremely good textbook. It is written in good language with good illustrations, and there is several sections here on high lift devices and flaps to be used on general aviation airplanes, and it's very highly recommended. An excellent presentation. Give a little idea of the kind of data and information that's in this book. Another recommended piece of literature is Fluid Dynamic Lift by Horner. This is available from the author's wife, and this book is an excellent presentation of a huge amount of data on high lift devices, wing planforms, and all of the various other factors influencing the amount of lift and lift capabilities of aerodynamic shapes. The author also has the equivalent of this book titled Fluid Dynamic Drag. That's actually his original work, and it is a collection of a tremendous amount of aerodynamic shapes illustrating the drag coefficients and various types of data on it. Both publications, both volumes are a must for anyone. You have to go through it slowly and carefully to gather all of the data that's being presented, but it is an excellent source of material.